So naive Bayes is a simple yet powerful model that could find its use in classification problems. It is robust and can serve as a handy baseline solution in dataset used for toying around with the data. So first off, let's recall the Bayes theorem, which is the backbone of this machine learning model. The naive Bayes theorem states that the probability of A given that B has already occurred equals to the probability of A multiplied by the probability of B given that A has already occurred divided by the probability of B. Now, the proof of this theorem is quite simple, but it is rather not intuitive, so let's quickly break it down. For that reason, let's recall that the probability of two events co-occurring equals to the product between the probability of A and the conditional probability of B given that A has occurred. And we can also rewrite this probability as a product of two other probabilities, which are the probability of B multiplied by the probability of A given that B has occurred. Well, the intuition behind these formulas, however, is not rather intuitive, but we can provide some overview as a form of an example where A would be an event of us winning a lottery and B would be an event of us becoming a millionaire. So since all of these two terms are fractions, the probability of A and B is pretty low, whereas the probability, the conditional probability of B given A or A given B is represented by a fraction. The probability of two events co-occurring divided by the P of A, or the same probability of two events co-occurring divided by the probability of B. Hence, this term would be bigger because we are dividing one small fraction over another bigger fraction, and in total this would result in a higher probability which goes along the actual reality we are observing. So the probability of two events co-occurring is really low. However, the conditional probability of us becoming a millionaire while we have already won a lottery or otherwise is actually pretty high. So this inequality is true. Or this is not a division operator, but rather just an OR. So in general, this is why this formula actually works in practice and it is actually applicable to real life problems. But it is just a general intuition of why this formula actually works. And there are many various examples which are quite logical and this formula satisfies them. So this could be an intuitive explanation as to why this formula works in real life. So given that we have defined these equalities, we can see that these are pretty much identities, and if we make an equality of them, if we make one term equal to another, we can represent this as a fraction between this, which would be the numerator term, and this, which would be the denominator term. So the probability of A given B would be equal to the probability of A multiplied by the probability of B given A divided by the probability of B. And hence, we got ourselves the proof for the Bayes theorem. So now, let's get back to the naive Bayes problem. What is the actual objective here? The problem we're trying to solve in naive Bayes is to find an unknown class of K given some observed sample X. Actually, observed sample X of I from a general training set of X, where X of I is represented by J features. So we have a table which is a set of samples x. We take x of I of here that contains j features representing each column in the dataset. And to write it more mathematically accurate, we need to find such k for an unobserved sample that maximizes the probability of this observed sample x of I belonging to the class C of k. And in fact, we can rewrite this term using the bias theorem we've explained above. So the probability of C of k given x of I is actually equal to the probability of x of I given C of k multiplied by the probability of C of k divided by the probability of x of I. So where does the naive part comes into play? You see, the probability of us observing a unique sample of x of I containing unique j features is really hard to calculate because we need to take into account numerous dependencies, features, attributes, and basically we need to know everything about the environment we operate in, which is impossible in most cases. That is why we naively assume that each event is independent, and hence we do not really need this term. The conditional probability can just be represented as a product between two probabilities. And hence, since we assume naively that the probabilities are independent, we can just represent this probability as a product of the two. The probability of observing xi given ck multiplied by the probability of observing the class k. So while this term is quite easy to calculate, so if we take a look at it, we need to find the probability of us observing the class k, which can be calculated as easy as dividing the size of the set of target variables, where target variables is basically a set of all classes corresponding to samples x of I. So we have some yi, which we take from this set of y containing different classes. So the set looks something like that. And we need to divide the number of elements in the set of y where the class is actually equal to an observed class C of k. And we need to divide it by the size of the set of all y's. So it's pretty easy to calculate, and we do not really know what should we do with this term. Well, let's get back to the naive part of the problem. And since we naively assume that all events are independent from one another, therefore each feature inside each sample is also independent from one another, because these are basically different random variables that we are looking at here. Since, as you remember, x of I consists of different x of j's, where each xj can be represented as a column. So it's a column value, and each column is basically its own random variable. Hence, since we naively assume that all events are independent from one another, that means that all random variables are also independent from one another, and we can represent this probability as a product of probabilities of each feature belonging to a class C of k. So what does that mean mathematically? That means that given some sample x of I, and given the assumption that all events are independent from one another, this probability can be represented as a product between the probability of us obtaining this class K multiplied by the product of all features from 1 to, let's call it m, of probabilities of obtaining this feature given that we are observing the class K. Now, we do not really know, we don't really know how to calculate this term because we do not know distributions inside each class. We cannot really assign x of m to some probability density function, and that is why the naive part extends to assumptions for this probability. Now, besides assuming that all events are independent from one another, so the simplest approach to this assumption would be assuming that distributions inside each class K, for example, if we have three classes, C1, C2, and C3, would follow a Gaussian distribution, some Gaussian distribution. And now, given this assumption, we can just plug this value inside the PDF of some C of k, and this would return the probability of observing x of m given that C of k has occurred. And there are multiple approaches to formulating these distributions. There's either Gaussian distributions or Bernoulli distributions. And you can find the full list of them on the Wikipedia page. So if you just Google naive Bayes classifier inside of Wikipedia and refer to the paragraph parameter estimation and event models, you can find all types of different naive Bayes models, including Gaussian naive Bayes, multinomial, Bernoulli, etc., etc. So there are multiple approaches that have been tested in the field, and you can just check them out on the Wikipedia page, which is quite convenient. Also, it's good to note that these assumptions about distributions inside each unique class are also called priors, and they are used in Bayesian statistics to also assume distributions inside unknown environment where data might have come from. Hence, it allows people to challenge someone else's prior, and it basically makes more room for challenging experiments and enhancements, and it makes statistics more fun. Now, let's code it up from scratch in pure numpy so we can understand all the inner workings of this naive Bayes model better. So the first step is actually importing numpy. Then we can define the model's class. Since we'll be doing the simplest approach to naive Bayes, which is a Gaussian naive Bayes, where we would just use the normal distribution, we will call it Gauss NB, where NB stands for naive Bayes. Now let's initialize this class. We don't actually pass any parameters here. However, inside of the initialization, we will create several attributes that could be accessible across all of class's methods. First off, let's initialize values, attributes for arrays of samples and their corresponding labels or classes, however you want to call them. Then we should create the array self.c, which will hold all possible unique classes across all samples. And then we create another array self-params, which will hold parameters for each unique class. And these parameters will hold information about mean and variance, which we will then plug into a normal distribution in order to find the probability, the conditional probability of us observing some feature inside a sample given some class C of k. So now we create a utility function which we can call the calc likelihood. And this function will basically tell us the likelihood of this particular feature belonging to a class C of k, exactly what we are trying to calculate over here. So this would mean that we're passing some feature xj, and we should also initialize epsilon in order to avoid divisions by 0. We can define epsilon as 1 to multiplied by 10 to the power of -6. And we should pass mu and var also, but should probably define them here. Now, this function in its turn would return the value inside the PDF function of the normal distribution. So we would just plug this xj inside the PDF of the normal distribution, and that will be that would mean basically calculating this probability. And recall that this probability, the PDF of C of k, given the Gaussian assumption, would mean that this scalar value would be calculated by this formula, 2 pi multiplied by variance, which is sigma squared of k, since each class has its unique variance or unique standard deviation. We can use these terms sigma squared and variance interchangeably, and we multiply this by the exponent of x of m. I believe x of m minus mu of k squared divided by 2 multiplied by sigma k squared, and I believe we should leave a minus over here. That is basically the formula that we would use in order to calculate this probability. And this is also the probability density function for the normal distribution. So this is exactly what we need to calculate over here. 2 multiplied by numpy.pi multiplied by variance multiplied by epsilon, because it is in the denominator of the fraction, and we don't really need to divide by zeros, since the program would just crash. And since it is in the denominator of the fraction, we need to raise this to the power of -0.5, and then we multiply this by numpy exponent of minus x minus mu squared divided by 2 multiplied by variance multiplied by epsilon once again in order to avoid division by 0. Now, no, x of j actually. Now we need to calculate the probability of observing class C of k, which is this term in our objective. And recall that this basically we pass all of these unique conditional probabilities inside this objective and find the class that maximizes this conditional probability. So the next step is calculating class probability, and here we'll just pass in the class k, and we return the mean of the logical array where target variables are equal to this class. So what does that actually mean, right? No pun intended over here. So in numpy, let's select another color. NumPy, this would be an array of different classes, right? Different observed classes corresponding to each value inside a general sample X. And this would be a scalar value. Basically, it could be 1, for example. So in total, this would result into another NumPy array, which will consist of true, false, false, etc. Because we are comparing each element inside of this array with this scalar value. So comparing 1 to 1 will result into true, 2 with 1 will result into false, and so on. And when we call the mean on top of this logical array, this would convert it to scalar values also, and true will correspond to 1, false to 0, and so on till the end. And hence the mean would mean that we are actually summing up all ones, which are basically all values inside our y, where the target value is equal to an observed class k, and we divide it, since we're calling the mean function, we are dividing it by n, where n is just the number of all target values, and it is in fact equal to the size of this set, which is y. So it is exactly the meaning of what we have written before, where we are basically calculating the value of this mathematical fraction. Using NumPy, we can just do it in one simple line of code. Alright, so now we need to calculate all posteriors for some sample, which then we will use an argmax function on and get the class that maximizes the posterior probability. So this would be another utility function with an underscore in the beginning. This would mean calculate posteriors. It will accept the parameter sample, which is basically x of I. So we should probably rename it to x of I in order to stay on track with the explanation we've described before. And now, first off, we need to create a posteriors array where we'll have an array of this would be C1 corresponding to the conditional probability of xi belonging to class 1, and this would be class 2 given that we are observing sample xi, and so on till class k. So this will be our array upon which we'll be calculating the argmax function. Now we need to iterate over each c of k, which will be initialized in the c attribute. First off, of course, we extract mu and var from the parameters attribute that we've also initialized in the beginning. So we've referred to the unique class by accessing as an index by just plugging in the actual c of k, and inside of this unique value corresponding to index c of k, we'll hold information about mu and variance. Now that I think of it, it's probably better for us to actually make params as a dictionary. That would make it just simply more readable. Then, since we are assuming that all events are independent, we just need to calculate the product, and for that reason, we should just need one variable that will hold the information about the whole posterior probability. So let's just create the posterior and initialize it with the probability of a class, basically the first term in this product. And then we iterate over each feature inside our sample x of I. So for x of j in x of I, we are extending our product by multiplying it with the calc likelihood function, where we pass x of j, mu, and var. And then we populate our posteriors with this unique posterior corresponding to class c of k. And that's pretty much it. Now we just need to return all of these posteriors, and we can actually finally define the fit predict function. Since this simple model does not actually need a learning cycle, as in with more sophisticated models such as logistic regression or softmax regression, we really just need to do everything, such as building up distributions and learning mu's and variances and other things in one go. So we just first of all initialize all of these attributes, self x and self y, with x and y that we pass in fit predict method. Then we populate the c attribute with all unique classes inside all possible target variables by just calling numpy.unique, and then we initialize the dictionary of self params, where each unique class c of k would correspond to a nested dictionary with keys mu, corresponding to a filtered array of x's, where their corresponding target variable is equal to c of k. And since it's a mu, we should take a mean, which is also just a simple import from numpy. And then we also need a key of variance, where it's the same, but we change mean to var. And then we need to iterate over each class in the previously defined attribute of c. So for c of k in self c. And that should do it for us. Oh, actually I've misplaced the iterative loop. Should be on the top, on the higher level than the nested dictionary. So now that we have defined all parameters, we've found all unique classes inside of our training set, we need to calculate all possible posteriors for each possible sample. So this would mean that we'll have an array of nested arrays of posteriors, which can be defined as a loop where we calculate posteriors of each x of I sample for x of I in the general set x. Actually, we can refer to the attributes of x just for good measure. And then we simply return for each unique sample x of I in the general training set x, we return the corresponding class, which can be found by putting argmax inside of our index that corresponds to the index of the array self.c, and we take argmax of a posterior for posterior in posteriors. So what does that actually, how does that actually help us? Let's break this code down really quick. Now, recall that we self-C, actually let's change the color. Self-C is an array of unique classes, and posteriors is actually, if we have 3 classes, let's do it like that, and so on. So it will be a nested array where each of these nested arrays would correspond to posteriors of basically x of I corresponding to of c of k corresponding to x of I. So this would mean that we are referring to the probability of us observing a certain class, either 1, 2, or 3, given that we are actually observing sample with the index of 1, then we'll have the same a nested array of the same size, which will refer to c of k given x of 2, the second sample from the general set of data, and so on. So this is a nested array of posteriors corresponding to a particular sample. And if we iterate over each posterior inside of these posteriors, this would mean that we are referring to this nested array, and argmax would mean just referring to the maximum argument inside of this array. So actually, it's a pretty good example. I believe that the argmax of this array, where we have 2 max probabilities, it would take the first occurring maximum element, and argmax of this array, 0.7 and 0.9, would actually return us 0, because this corresponds to the 0 index inside of this array. And basically, this argmax of 0 would, in its turn, refer to the 0 element inside all of these unique classes, and hence it will return, all of this will return 1, because class of 1, which has an index of 0, has the maximum probability of occurring for sample x of 1. And same logic goes for x of 2, x of 3, and so on to n. That is basically what this generator loop means. And we're pretty much done with this model. Now we can create a toy dataset. For that reason, we will import modules such as matplotlib in order to visualize the data better. Then we import pandas as PD for us to just operate the data in a more concise way without using too much transformations. And we would add Seaborn just to add some useful functionality for plotting and displaying data, which will be a scatter plot because we'll have just 2 classes and each sample would consist of just 2 features. So it would be pretty easy to understand. Now, having said that, we will define the general set X as a set of samples consisting of 2 features. The first one would be -1, -1. The second one would be -2, -1. Third one would be -3, -2, for example. This one would be 1, 1. This one would be 2, 1. And this one would be, so it would be a little bit higher than the last one, 3, 2. And their corresponding target variables would be 1, 1, 1, and next 3 also have the same class. Now we build the train data frame by referring to the data frame API inside pandas, where we pass a list of zipped elements of x and y, and in order to automatically label these features as columns, we also pass in the columns argument where we label axes as x's and target variables or classes as y's. Now we should break down our x, since if we just display it like that, this would be a nested list inside of this column, which is rather inconvenient. So we should probably break this column x into 2 features, x1 and x2, by using a very convenient API that pandas yet again offers to us. So we just refer to column x, refer to attribute str, and extract the first element in each value inside of this column x, and that would mean referring to the first element inside of each of these lists. And same goes for the second feature, but we change the index from 0 to 1. And since we've broken down our column x, we don't really need it, so we can just drop it just like that by passing x as a column and in place true, since we are not reinitializing our train data frame. Now, since the plot in general is going to be pretty big, we need to change its size by accessing the inner API of matplotlib, by accessing the POT module and its RC params attribute, where we then refer to figure.fixSize, where we can tweak the general figure size for each matplotlib plot. So we can select something as small as 5.3, where 5 would correspond to width and 3 would correspond to height. And then we would use the Seaborn API in order to get a good visualization with all beautiful styles Seaborn has to offer. So for that reason, we just pass train data frame to data parameter. X would be the first feature, Y would be the second feature, and we would label these points by their class values. And that will result in this beautiful plot where we can observe all of these values of 2 features each. So let's actually use our coded up model. So Gaussian NB dot fit predict. Since our model and our class is not sophisticated enough, we don't really need to separately initialize it. We can just do it in one simple line. Then we need to convert our x into a numpy array, because otherwise it would result in the error, because we're calling a bunch of methods that are only present in the numpy API. So now we should also do the same to a set of target variables. And now if we run this model on this data, this would result into exactly what we have defined here. So the model works pretty well on a simple data set such as like this. And just as a double check, we can now compare our own implementation with the one that is present inside scikit-learn. So just import Gaussian naive Bayes from naive Bayes module. Then we should separately initialize the model as, for example, CLF classifier. And then we do, first of all, fit method on top of our data, which we don't really need to transform because scikit-learn has everything covered. It transforms lists into numpy arrays automatically. And then we just do predict on the same data, which results into same predictions. So our implementation is on par in terms of predictions quality for this data with the scikit-learn implementation.